In this video, we're going to have a brief review of some of the important results for magnetic field calculations. So we'll talk about geometries, current carrying wire, the center of a current loop, on the central axis of a current loop at a distance r from the center, magnetic field of a solenoid as well as a toroid. So before we do that, I would like to start with another remark about unit systems. This has to do with a factor of 1 over c appearing in most texts. So when you read some books about magnetism, you may find that, especially in old books, a factor of 1 over c, where c is the speed of light, appears in most texts. So where does this factor of 1 over c comes from? This is due to the choice of the unit system being electrostatic CGS. Okay, so basically we have in electrostatic CGS, for example, the charge of an electron is 1.6 10 to minus 19 coulombs in SI, is in electrostatic CGS units 4.8 10 to minus 10 electrostatic units. One electrostatic unit is 3.336 10 to minus 10 coulombs, but that's not the best way to remember these units. 1 amp of current is 3 times 10 to 9 electrostatic units per second. So if you would like to remember how to go in between SI and electrostatic units, this is what I would recommend that you remember. The 1 amp is 3 times 10 to 9 ESU per second. 3 times 10 to 8 is speed of light, so it's like 10 times the value of the speed of light. Electrostatic units per second. So in this case, you will find that if you are using electrostatic units per second for current, for the current carrying wire, when we are looking at the magnetic field outside, H of R greater than capital R would be given by not 2I over R but 2I over CR, where C is the speed of light. So if you want to check this for 1 amp current, R is equal to 1 meter, and H is going to be given in Ørsted again. So H was in amps per meter in SI units. So remember that our result was H is I over 2 pi R in SI, and that gives us 1 amp divided by 2 pi amps per meter, which corresponds to 2 milli Ørsted we have found, because 1 Ørsted is 1000 divided by 4 pi amps per meter, or 79.6 amps per meter roughly. So let's check if this result works here using the electrostatic CGS units. Now the speed of light, C, is 3 times 10 to 10 centimeters per second. R is 100 centimeters in electrostatic CGS units. 1 amp is 3 times 10 to 9 electrostatic units per second. So if you substitute these values, you will find that H is equal to 3 times 10 to 9 divided by 3 times 3 times 10 to 9 times 2, 3 times 10 to 10, and then 100 centimeters. So this will give us 2 millierstads as well. So you need this additional factor of C. And similarly, using electrostatic CGS units, remember Ampere's law. Ampere's law was in SI units, H dot dl is equal to I, that's SI. H dot dl is equal to 4 pi I using electromagnetic units, which is the choice we have usually. But in electrostatic CGS units, you would have H dot dl is equal to 4 pi I over C. So that is CGS electrostatic units. So you can see that in these field calculations, an easy way to go between unit systems is the current is going to be replaced with 4 pi times the current in electromagnetic CGS units. It will be replaced with 4 pi over C times the current in electrostatic units. We're going from amps to ab amps, and then we're going to electrostatic units per second for current. And you need to know the conversion between these. 1 ab amp is equal to 10 amps, and 1 amp is equal to 3 times 10 to 9 electrostatic units per second. So that's how we can remember. Okay, so let's take a look at our results for most interesting geometries. You can verify these using Ampere's law whenever applicable, or you can use Biot-Savart law as we have demonstrated in the previous videos. Okay, so once again, the magnetic field due to a current carrying wire. So if you have a radial distance r, so let's call the wire radius capital R, we have shown that the magnetic field H for R greater than R is I divided by 2 pi R. In SI it is 2I divided by R. In CGS EMU it is 2I divided by CR in CGS electrostatic units. So once again, in SI we have current in amps, R in meters. In CGS EMU, current in ab amps, R in centimeters. In CGS ESU, current in electrostatic units per second, and R in centimeters. And H will turn out to be in amps per meter in SI. In the CGS units, it will be given in Ørsted. So the results for the magnetic field inside the wire for R less than capital R, you can go back and see what we have obtained using Ampere's law. It was for the wire IR divided by 2 pi R squared. So the answer was IR divided by 2 pi R squared, capital R squared, for R less than R in SI. Now you can easily convert this to CGS EMU. All you have to do is replace your I with 4 pi I, so that you will obtain 2I over R divided by R squared, and here you will have 2I over CR, capital R squared times R in CGS ESU units if you wish. But once again, we're mainly interested in electromagnetic units in our calculations. Now, magnetic field at the center of a coil. So if you calculate the magnetic field at the center of a coil, it turns out to be in SI units I divided by 2R, where R is the radius of the coil. So if I want to write this in CGS EMU units, I replaced I with 4 pi I, so that the answer becomes 2 pi I over R in CGS EMU, and it becomes 2 pi I over CR in CGS ESU units. So once again, you have to be careful. Here the current is in amps. Here the current is in electrostatic units per second. Here R is in centimeters, R is in centimeters. And here we have current in amps, R in meters, H in amps per meter. Here H is in Ørsted, H is in Ørsted. Okay. Field on the axis of a central axis of a coil. So if I'm at a distance R from the axis, so let's say that the radius of this is this coil is capital R, and I'm at a distance R from the central axis. So what would be the magnetic field at this point? The magnetic field, first of all, you can find its direction using the right hand rule. The magnetic field in this configuration would point in the positive Z direction. So that would be my H. And the magnetic field value or magnetic field strength in SI units will be I capital R squared divided by 2 R squared plus capital R squared to the power 3 over 2. This is in SI. Now let's write the same result in electromagnetic CGS units. I replace I with 4 pi I, so it's going to become 2 pi I R squared divided by R squared plus capital R squared to 3 to the power 3.5 CGS EMU, and the same result, 2 pi I R squared divided by C R squared plus capital R squared to the power 3/2 for CGS electrostatic units. So you can see that it goes as, for R much greater than capital R, it goes as 1 over R, for example. So you can see the limits of this magnetic field for different R values. So capital R is the coil radius, and R distance from the center. On the central axis. Okay. How about the magnetic field inside a solenoid? So if the solenoid has n turns per unit length, so n I call turns per unit length, so it's a bunch of coils, current carrying coils that are wrapped around this material. And you can see that you can use your right hand rule, you curl your fingers around the current, your thumb points in the direction of the magnetic field. so that you would see the field lines would come out from one end and approach the other end. So one end will act like the North Pole, the other end will act like the South Pole. And the magnetic field inside the solenoid is given as N times I. So this is SI units inside the solenoid. And in CGS EMU units, it's going to become 4 pi Ni. And in electrostatic units, it will become 4 pi over C Ni. Okay, so that's a simple exercise. And finally, for the toroid, where we bend a solenoid to form a loop, we have once again the magnetic field inside will be given by, because it's simply a solenoid, is number of turns times the current in SI, but the number of turns will be total number of turns, capital N, divided by 2 pi r, where r is the radius of the toroid. So you can see here this r is the radius of the toroid, and multiplied with I. So this is SI. Capital N is total number of turns, and in CGS EMU units this will be 4 pi Ni, which will be equal to 2 Ni over R in CGS EMU, and it will be equal to 2 Ni over Cr in CGS electrostatic units. Okay, so these results we have to be aware of because we use them frequently, so we have to remember these results. Once again, you can verify them using Ampere's law or Biot-Savart law wherever applicable. So we have started out by a remark. We talked about electrostatic CGS units because occasionally we see a factor of 1 over C appearing in our expressions for the magnetic fields in most texts. That comes from using electrostatic CGS units where 1 amp is 3 times 10 to 9 electrostatic units per second. So using electrostatic units, we see that Ampere's law is modified to be H.dl closed loop integral is 4 pi I over C, and for example, for the magnetic field outside the current carrying wire, we have, instead of 2I over R in electromagnetic CGS units, 2I over CR. So a shortcut to go between unit systems here is to replace I with 4 pi I or 4 pi over Ci for the electrostatic CGS units. But you have to be careful. Here current is in amps in SI, amps in EMU, and electrostatic units per seconds in ESU CGS units. And the conversion is 1 amp is 10 amps and 1 amp is 3 times 10 to 9 ESU per second. Now, with these, we can see that the magnetic field due to a current carrying wire outside varies as 1 over R, I over 2 pi R, 2I over R, or 2I over CR. And inside it varies linearly with R, IR over 2 pi capital R squared, 2IR over capital R squared, or 2I over C capital R squared times R. So once again, C is speed of light. And you may want to remember that the speed of light C from your electromagnetism course is 1 over square root mu 0 epsilon 0. Permittivity of free space and permeability of free space. So for magnetic field at the center of a coil, the magnetic field varies as 1 over R, the radius of the coil. It's I over 2R for SI, 2 pi I over R for EMU, 2 pi I over CR for ESU. If we are at a distance r from a coil with radius capital R, the magnetic field at the center can be found easily using symmetry of current elements using Biot-Savart law, for example, is I capital R squared divided by 2 parentheses R squared plus capital R squared to the power 3 half. We replace I with 4 pi I for CGSEMU, so instead of IR squared, it's 2 pi R squared, or 2 pi IR squared over C for ESU. Inside the solenoid, where we have n turns per length, the magnetic field inside is Ni, 4 pi Ni or 4 pi Ni over C, depending on the unit system, and the way the magnetic field lines point using your right hand rule, you can see that one end is acting like the North Pole, the other one is acting like the South Pole. If you bring the North and South together, you have a continuous flux of magnetic field inside a toroid, which has, of course, because it's a solenoid, it's also n times I, the magnetic field inside, but it is total number of turns divided by 2 pi R, because that's the length times I. So you have 2 Ni over R for EMU, 2 Ni over CR for ESU unit system.